We'd like to welcome everyone to the 11th session of Geometry and Tacos, where this time around we're going to be talking about ideas in Weisman geometry and locally conformally Kähler geometry more generally. Today we have some introductory lectures that we are very grateful to have Professor Liviu Ornea from the University of Bucharest, who will be talking to us about these concepts, so that we'll be really well posed to understand the lectures in the next couple of days. So, Liviu, please take it away.
Thank you. I prepared these talks, introductory talks, starting from scratch. And in the first one, I won't give, I think, any proof. I'll just describe things, give you results and comments. And it will be mainly about definitions of LCK manifolds and the most important classes. And I shall end this first talk with Weisman geometry. And in the second introductory talk, it will be a bit more involved, and I shall concentrate on LCK with potential. There will be eventually some proofs. So please feel free to ask during the talk. Okay, so let's start with the definitions, even if I suppose many of you know it. I shall describe several definitions and try to explain the equivalence between them. The context is complex manifold, not curves, which are Kähler. We are trying to do this geometry in the absence of Kähler structures. So this is interesting, mainly on compact manifolds, where you don't have Kähler structures. So it will be a Hermitian manifold I denote with I in the complex structure, which I suppose to be integrable. Also, you can also do some almost complex geometry with locally conformally Kähler structure. And the convention for the fundamental two form is the one I have written. I put I on the first argument. This is the tensorial definition. Is just an integrability condition for the two form, which is no more closed. But it depends on a Lie form, the so-called Lie form, because it appeared first in the paper of Lie. That was in 1943. Then, with the work of mainly of Paul Gauduchon, this Lie form can be interpreted as the torsion form of the Chern connection. You know, his famous paper about Matt-Allen paper in 1980. But for us, this will be the definition. From dimensions 3 on, you don't even need to put the closeness condition. It follows, but let's put it to have a unitary definition for surfaces and for higher dimensional manifolds. Of course, we don't want theta to be exact. When it is exact, we talk about globally conformally Kähler. And there is the version without complex structure, which is called locally conformally symplectic, which is a field of interest in its own. It seems there are more LCS than LCK. I will tell you more in the next slide. the definition as it is given here, it's clearly conformal invariant. So this places this geometry at the border between conformal geometry and complex geometry. And obviously, complex submanifolds, if they exist, they inherit the structure. Let's forget about curves. This is, of course, another thing. Curves are scalar, so it's more difficult to talk about to analyze curves, existence of curves in LCK, in compact LCKs. There is this characterization in terms of currents, which is the analog of Lawson, Harvey Lawson characterization of Kähler, which was then, well, I think it originated in Sullivan. But it was then adapted also by Michelson to balanced. So, but it exists also for LCK. You can see it here. Alexandra proved this in her master thesis, and up to now I didn't see this characterization used, but I think it's important to have it and to mention it. LCK currents in LCK geometry are important and will come into discussion later on. Now there is this open question. Find compact LCS manifolds which do not admit LCK structure. This is, of course, the analog of find symplectic manifolds which are not Kähler. It wasn't very easy to solve in the Kähler case. It seems even more difficult in the LCK case. As far as I know, there are only examples in dimension 4 and in real dimension 4, yeah. And this is done by using heavily the classification of complex surfaces. Well, I don't think it's satisfactory. It wasn't proved that in higher dimension every LCS can have compatible LCK structure. And on the other hand, there is no counterexample, as far as I know. So we gave it still as an open question in our book, Advertising Moment. We have a book with Misha Verbitsky on this topic. I think Ethan is the only one who read it, but us, of course. So this is still an open question. There is a criterion given by Eliashberg and Murphy for LCS, topological criterion, which is rather obvious. You should have B1 positive and something rational in the cohomology, in the one cohomology. But this doesn't ensure the existence of LCK. Any questions for this So up to now, we have this first definition, d omega equal theta wedge omega with d theta closed.
Uh, could you, I had a question in the previous page.
Yes.
Can you go like one further page back?
Here?
No, the next page. Yes,
Okay.
so here in the theorem, when I say that mi theta is a complex manifold, uh,
Yes.
I is the usual complex structure, right?
Yes. Yes.
And so, okay, I see. No, I was just confused. Now it's clear. Yeah, okay.
Okay. I didn't introduce before, but here it is given d theta is this twisted differential. We shall discuss later. So
Okay.
is it okay?
Yes, no, it's okay. Yeah.
Good. So the second definition is, say, the geometric one, is the one which motivates the name. You just need an atlas, and on each open set of the atlas, a Kähler form such that the transition functions are homosthetes. You may ask that the transition functions be conformal, but conformal between two symplectic forms are necessarily homosthetes in dimension greater than 2. So you can ask from the beginning to be homosthetes. And you can show without problem that when you have such local Kähler structures, you cannot glue these Kähler structures, but you can modify conformally each one so that this conformal Kähler, local conformal Kähler structures to be glued to an LCK form, which restricts to the local ones. So that's the definition of the geometric definition, say. This definition is easily moved to the universal cover, or it appears like this in Vaisman, explicitly or implicitly. Vaisman really gives just the definition with d omega equals theta wedge omega. But then he comments, and in subsequent papers, you find this as a remark. Of course, you don't need to look necessarily at the universal cover. You can just stick to, you can ask the existence of a cover together with a Kähler form and the deck group acting by Kähler homosthetes. And then, of course, you will have the same thing on the universal cover and so on. That's the viewpoint that we adopt mainly in the work with Misha. And most of what I did is together with Misha Verbitsky, and this is we think this is the good point, the good point of view, especially good for LCK with potential. This definition allows defining some other objects intimately associated. The first one is this homothetic character. It just associates to, well, this is a mistake here, to to a deck group, to an element of the deck group, the scale factor given by this homosity. So you identify an element, you identify the deck group with a subgroup of automorphisms. There are homocities, and each homocity has a scale factor, which is a positive number. You have this homomorphism, and it is important to understand its image in R plus. On one hand, and on the other hand, it is important to look at objects which behave well with respect to this deck group. The ones we are interested in are the differential forms, which we call automorphic. If you can control their behavior, the good behavior is this one. They multiply the differential form by the homocity character. Valid also for functions, of course. An object which is automorphic will be interpreted immediately as a section in a certain bundle. As I said, you don't have only the universal cover, you can have many subcovers with scalar form and the deck group acting by homocities, and we are interested in the extreme ones, the universal cover and the minimal cover. The minimal cover corresponds to a deck group with no isometries. The homocity character then will be injective. Many constructions can be reduced to the minimal cover. You get rid of the unnecessary isometries that you may have on the universal cover. Another invariant which is important is the rank of the character, of the image, of the rank of the character, that is the rank of this subgroup image of chi in R plus. We call it the LCK rank. Of course, when the LCK rank is 1, then you have an action of the integer group, which is very, very useful. So many times the battle is the struggle is to find an LCK structure of rank 1. We shall come back to this. Any questions about this definition with the scalar cover? Okay. This is a notion, the weight bundle is a notion coming from conformal geometry. This doesn't appear in Vaisman papers. It was understood later on, gradually, and it is related to the previous definition. So, if you have this representation of the deck group, that is, you have a representation of pi 1, the fundamental group of your LCK manifold. You associate a line bundle, the local system, and the Lie form theta can be interpreted as a flat connection in this line bundle. Then this group, the image of chi, whose rank is the LCK rank, is the monodromy of this flat connection. The minimal cover can be then characterized by the pullback of this bundle being trivial. On the other hand, the name weight bundle comes from conformal geometry. Again, this is very well explained in Gauduchon papers. It is the bundle of conformal weights. So it encodes the conformal geometry of an LCK manifold, and also via the Lie form, the connection, it encodes also the complex geometry here. This characterization, which can stay as a definition also, this was new. It wasn't in the papers of Vaisman. It is very easy to show that if M is LCK, this bundle exists. You form it as I told you. The converse is much more difficult. I mean, it is difficult if you just start with a complex manifold and with this flat line bundle. It's not easy to construct everything, to recompose the metric in the conformal class. It can be done. And once you understand this correspondence between LCK structure and this weight bundle, you understand also, I go back to automorphic, that automorphic objects on the universal cover can be understood as sections of this weight bundle. Also, this bundle is very useful to introduce the so-called twisted cohomology, Morse-Novikov cohomology, whatever. The topologists hate me for this Morse-Novikov because they say that it's not Morse-Novikov cohomology, that it's trivial to associate Morse-Novikov cohomology to a global closed form. But a lot of people call it like this. Others call it Lishnerovich cohomology or twisted, just twisted. So it is the cohomology of d theta. This operator clearly has null square. So it gives a cohomology which is finite dimensional, etc. It's elliptic complex, so it gives a good finite dimensional cohomology, but it also corresponds to the cohomology of M with values in this local system. And sometimes it is very useful to see it like this. Especially when there is another thing that we shall talk maybe later on, but I want to tell you now. This geometry appears on manifolds, on complex manifolds, which are very far from being algebraic. They are non-Kähler, so they won't be algebraic. However, there are tools to link this kind of geometry to algebraic geometry, especially to projective manifolds or orbifolds. And this weight bundle, which will be almost positive, is one of the tools we employ. Now, let me give you examples. First examples were given by Vaisman on the Hopf manifolds, on diagonal Hopf manifolds, not diagonal, sorry. Hopf manifolds obtained by quotienting to multiple of the identity operator. So Cn minus 0 quotiented to the group generated by Z goes to 2Z, something like this. But very, very soon, non-scalar compact complex surfaces came into the game, and almost all proved to be LCK. The first examples were Vaisman, Tricheri, a very important paper on surfaces, on the Inoue surfaces. Then I helped Gaudichon for all Hopf surfaces, diagonal or not. Belgun, who proved that, who classified the Weissman ones. I shall give further definition. Brunella, who proved that Enoki surfaces first, and then all Kato surfaces are LCK. There is a great deal of work even now on LCK surfaces and yeah, in general on compact complex surfaces. But for LCK, these are the names to follow. Of course, Brunella, you cannot follow him anymore, but working now, Apostolov and Lusky, they have a lot of, they are interested in locally conformally symplectic surfaces, taming complex surfaces, complex structures. Fujiki, Pontecorvo, Gaudichon, of course, Otiman, many work still on surfaces. In general, a Hopf manifold is defined as the quotient of Cn minus 0 by the cyclic group generated by a holomorphic contraction at 0. The first examples of Hopf manifolds, which are LCK, were when the contraction is linear. And these are called linear Hopf manifolds. But Weissman doesn't bother to call them linear because they were almost the only ones studied. Kodaira classifies, he has linear and nonlinear Hopf surfaces. And the problem is in the end, to show that even the nonlinear Hopf are LCK. And this was done only recently, 2-3 years ago, by Misha and me. I shall explain how. So now we know that all Hopf manifolds with the contraction linear or not are example of LCKs. Some of the Kato manifolds, I won't enter into details in Alexandra's talk. She will explain better what Kato manifolds are. They generalize the Kato surfaces to higher dimensions. Kato surfaces are the ones having a global spherical shell. The global spherical shell is an immersion of is an open set containing an S3 and which doesn't disconnect the surface. And Kato and then Dlusky characterized them as modifications of Hopf manifolds. That's for the surfaces. In higher dimension, there are two papers by, one paper is Stratio-Otiman Pontecorvo, where the LCK structure is described on some of the Kato manifolds, and then a second one is Ruggiero as a fourth author when they discuss further properties of what they call toric Kato manifolds. So since Brunella showed that all Kato surfaces are LCK, if the global spherical shell conjecture, not conjecture, is true, we have LCK on all non-Kähler compact surfaces, but of the only missing one is a type of Inoue S plus with some parameters on which Belgun has shown that there is no LCK structure. We shall discuss more the implications of this finding of Florin Belgun. Another example that is important, and I shall need it. So even if Alexandra will give more details about construction, I shall give a bit here. Is these early Klaus-Thoma manifolds introduced in 2015 as a generalization of the first class of Inoue surfaces, S plus. They are associated to a number field with some complex embeddings to T and some real embeddings. And digging a bit in number theory, you take this group of positive integers, OK plus, OK star plus, and they show that there exists a free abelian subgroup of rank exactly S, such that to have a compact quotient from the real part, and then they form this group, this strange group, a semi-direct product here, and construct an action on an affine action on CT times HS. So in fact, what you should remember is that the early Klaus-Thoma manifolds are quotients of CT times HS, when H is the Poincare half plane, where this gamma, which is the semi-direct product of OK plus and the invertible elements in the field, act by affine transformation, by translations and by homostates. So the complex embeddings act by translations only, and the real ones by homostates also. You obtain an affine manifold which was proven to be non-Kähler. And it admits LCK metric only when the cover is C times HS. Earlier, Klaus and Thomas showed that when T is 1, the manifold admits LCK metric. Then Diacono and Vuletescu showed that it's only when T equal 1. So now it's clear that they have LCK metric only when, if and only if T equal 1. It is not quite a geometrical proof, it's a number theoretical proof. I think Kasuya showed that they are solved manifolds, which is natural because Inoue surfaces are solved manifolds. And also the Tricheri, the metric that Tricheri found on Inoue surfaces was generalized here by Elie Klaus and Thomas. I need it, so I shall explain what is the metric. Now we deal only with LCK OT manifold, so C times HS mod this, oh, I'm sorry, mod this affine group. And we take a potential, this phi. W are the coordinates on the Poincare half plane, so the imaginary part is strictly positive. You take this potential, which generalizes exactly the potential given by Tricheri. And what happens is that this potential is not automorphic, but DDC of it is automorphic. So this is the usual way in which you construct LCK metrics. You try to find a Kähler metric which is automorphic. And the easiest way to find a Kähler metric automorphic on the universal cover is to take DDC of something, an exact one. Only you sometimes it happens that the potential is automorphic. That's very rare. Usually the potential is not, as in this case. The Lie form can be then written explicitly minus d log of this denominator, product of the images W. And what Otiman showed or Otiman and Istrati showed, I think, and Otiman for Inoue and Istrati Otiman for OTs, is that the Lie class, the class of the Lie form, is unique in H1. That's a problem that I shall deal with maybe in the next talk. When you have an LCK manifold, you are interested to know how large is the subset of H1 of the first cohomology formed by possible Lie forms. And for Inoue, there is a singleton. For Elie Klaus Thomas, again a singleton. In other cases, you can have a half space. This formula maybe we shall use dc of theta. By dc, I denote the real del bar, say, is minus I di. Okay, so far for the Elie Klaus Thomas manifold, they are very, very useful examples, especially because being associated to number fields, you can compute, you can test and compute a lot of things starting from well chosen polynomials. These are the, as far as I know, at this moment some concrete examples of complex compact manifolds which cannot have LCK structure. Why is it important? Because we don't have, as in the Kähler case, a list of topological obstructions. For the general LCK case, we don't have such a list. So it's important to have specific examples when we know with different kind of proofs that there is no LCK metric. For example, for this, surfaces, the S plus surfaces depend of several parameters, and for a specific choice of the parameters, Tricheri wasn't able to produce a metric, an LCK metric. And then that was in 82 or 84. And Belgun in 2000 showed that Tricheri wasn't able to find it because it wasn't possible. Unfortunately, Tricheri is dead in 95, and he couldn't see this. Belgun's method was very nice and inaugurated a series of proofs in other cases which mimic his idea. He showed that once you have an LCK structure on these surfaces, then you have also an invariant one. Remember that they are solved manifolds. So that's a trick which works there on these surfaces and on other solved manifolds. And then he showed that invariant structures you cannot have by a very clever computation. More recently, I think 5 years ago or something like this, this kind of new manifolds appeared. We called them Endo-Pajitnov because they were defined by these two guys in a paper. Again, solved manifolds and again generalization of Inouye surfaces S0, but different from earlier Clauss-Thoma. So you can generalize in higher dimension the Inouye surfaces in several ways. There is another one, another generalization given by Petcu recently. I suppose there will be others. So these Endo-Pajitnov manifolds, they are again associated to matrices, matrices from, in this case, from SL to N plus 1 Z. But the construction is rather involved. I won't describe it. If you want to look, they are described in Endo-Pajitnov paper, and also in a more recent paper by Chuliko, Otiman, and Stanchu, in which also the metrics are described. And they are very interesting because they could prove that they can bear no LCK metric. Instead, they cannot have balanced metric. Instead, they have pluriclosed metrics and other types. So this is for the moment what we know about having no LCK structure. Of course, you can imagine some trivial obstructions regarding the pi1, which cannot be a product of subgroups of different index, for example, because it won't enter well in R plus by the homothetic character. And but these are trivial obstructions, and I didn't see any paper using them to produce something. I try to describe now the geometry and results on LCK manifolds. Oh, I'm sorry, I'm late. So this is one of the most important theorems in the beginning, and still it is. Vaisman theorem stating that if you already have a Kähler metric, then any LCK metric is again globally conformally Kähler. So you cannot have strict LCK and Kähler. That is why compact LCK manifolds are important, not open ones. And the proof uses essentially the DDC lemma, which was then generalized a bit by Angela Ugarte in this way, using Bott-Chern cohomology, the map, natural map from Bott-Chern to Dolbeau cohomology. It's a bit of generalization of DDC lemma. The whole theory of LCK manifolds was extended to spaces with singularities in a series of papers by Preda and Stancio. Rather difficult papers because you don't even have a well-established notion of Kähler form on spaces. And the same theorem was also extended recently to locally conformally symplectic geometry by Lejmi and Wilson. It's a mistake here. This is the form that in which they extended it. It's not exactly the statement, Vaisman statement, but the idea is there. So they need, instead of DD bar, they need hard Lefschetz. If you want a summary comparison between Kähler and LCK, when you look at the properties of Kähler, first, the blow up at points, it is preserved also in LCK case, the statement and a simile proof was given by Triceri. The proof was then made correct by Vuletescu many years after that. The blow up along submanifolds is not preserved as in the Kähler case, but only if the submanifold, the Lie form restricted to the submanifold has to be exact. Stability at small deformation, certainly no, because this is the way in which Belgun showed that because since Belgun showed that some Inoue surfaces are not LCK, and we knew that the others are, and they can be deformed one into the other from the complex viewpoint, it's clear that we have no stability. But some particular subclass, which will be my main focus after that, is LCK with potential. They are stable. You have this well-known theorem about killing and holomorphic fields on Kähler, and this still holds. It was a surprise. it's Moroianu and Pilka, Andrei Moroianu, on compact manifolds which are not Hopf and are not locally conformally hyperkähler. This simple obstruction in Kähler, for many years, it was asked by Vaisman in the LCK case, and it was thought to be true, but early Klaus and Thoma found explicitly in their paper a threefold in which all Betty numbers are even. As regards the Kähler-Einstein and the extremal metrics business, in LCK case, it is this very powerful theorem by Madani, Moroianu, and Pilka that they cannot be Einstein. That's very difficult proof, very involved. And the suitable notion then is Einstein-Weil. You should refer to the Weil connection, kind of Einstein condition in the weight bundle. And this implies Vaisman and Calabi-Yau cover. So we enter into a narrower street. And complex submanifolds are minimal in Kähler. Here it is not the case. You have to take into account the mean curvature vector. It is instead in Vaisman manifolds the situation is better. The fact that complex manifolds are not minimal automatically opens place for discussing Harvey-Lawson type theories in LCK, which is for the moment not discussed. Okay. I'd like to pass to Vaisman. I don't know if I have to stop. Ethan?
Yeah, if you think this is a good point, you could pick this up.
As you say, as you want. I can stop now. I can go further.
You can finish the first presentation,
Okay.
and then we'll take a
Then
break.
let's go on to Vaisman, and I try to move quicker. So the definition of Vaisman is that you have an LCK and the Lie form is parallel with respect to the Levi-Civita connection. So you give a condition of holonomy, in fact, and with this condition you exit the realm of conformal geometry, because this is not conformally invariant. And of course, nabla theta equals 0 implies the codifferential of theta equals 0. But codifferential of theta equals 0 is exactly the definition of the Gaudichon metric. The Gaudichon metric exists and is unique in every conformal class. So if you have a Vaisman metric, it is unique in its conformal class as being Gaudichon. You cannot have more different Vaisman metrics in a conformal class. Examples of Vaisman manifolds are the diagonal Hopf manifolds. These were the first examples. Vaisman introduced this manifolds as generalized Hopf, but the name was already in use in algebraic geometry, so we changed it, gave his name. But if you look at the first papers until 98 or 2000, it's full of generalized Hopf manifolds. And then we proved that a Hopf manifold is Weisman if and only if it is a diagonal Hopf. Compact complex submanifolds in Weisman are again Weisman because, as we shall see, they are tangent to the Lie field. In surfaces, you have non-Kähler elliptic surfaces also. And it's important that you can deform Weisman manifolds to obtain other Weisman manifolds. Not any deformation preserves the class, but there are deformations preserving the class. Among the LCK, which are non-Weisman, of course, non-diagonal Hopf manifolds, all the Inoue surfaces, and then the Kato manifolds, OT manifolds, and the blow-ups of LCK. Because of the characteristic. On Weisman, you have by this condition, theta has constant length, so the Lie field cannot be zero, cannot have zeros. So the characteristic is zero. On Weisman manifolds, the main tool is this canonical foliation. It is generated by the Lie field and it's orthogonal. By direct computation, we can prove that they commute, they are killing and holomorphic. So they generate a foliation. This foliation proves to be Riemannian and totally geodesic. These were facts known to Weisman already. Now, when you have a foliation and you come from topology, you look at regular foliation, or at least you look to quasi-regular foliation. There are competing definitions. We prefer this one. Quasi-regular means compact leaves. In particular, there exists a leaf space which is an orbifold. In this case, it will be projective because you just kill the part depending on theta and I theta, and what remains is a Kähler metric. But this fact was astonishing, that if you fix the complex structure and you have two different Weisman metrics, then the Lie fields are collinear by constant factor. And this tells you that the canonical foliation only depends on the complex structure. It's by no means obvious. Tsukada was the first to find this. Then there are many, many proofs after that. You can show that compact complex subvarieties, not only submanifolds, are tangent to the canonical foliation. And see, by this formula, you see that when you kill theta, you arrive at something that we call omega zero, this DC theta, which is positive on the orthogonal of the foliation. So this form, DC theta, is almost positive, as I said. It has only one complex direction in which it vanishes. In the rest, it is positive. And you can identify it with the curvature of the Chern connection in the weight bundle complexified. And now you have an ample bundle on Weisman. And that's what I was telling you, that you can go from LCK to algebraic geometry by using the weight bundle. There are different characterizations of Weisman manifolds among the LCK manifolds. The oldest, I suppose, is this one. You need a holomorphic and conformal flow, complex flow, without fixed points, and which lifts to two homotheties on the Kähler cover. And then the manifold is of Weismann type. The idea of the proof was to go on the universal cover and having from this lifted flow to construct a decomposition of the universal cover into Sasakian manifold and R and the line. As in the case of the Hopf, to mimic what happens in the Hopf, where the cover is sphere, odd dimension sphere and R. And from the proof, you see that the coordinate on the line is exactly the potential. The square of the coordinate is the potential, which gives you the LCK structure. The theorem was generalized very nicely by Istrati using a torus action. Not exactly a generalization, but it's in the same spirit. Her condition was that he calls the kind of torus a totally real torus. I just want to give you this structure theorem. You remember the LCK rank is the rank of the image of the homoscedastic character, and when the LCK rank is 1, it means that grosso modo you can say that the deck group is Z, the integers. So for this kind of Weismann manifolds, which are quotients of something of a Kähler manifold by Z, they can be obtained by this receipt. I hope you know what a Sasakian manifold is. So you take its Kähler cone with the cone metric, you take a homoscedasty along the generators, and then you obtain a Weismann manifold by quotienting to the cyclic group generated by that homoscedasty. And it's not restrictive, the condition on the rank, because we proved that you can always deform a Weismann manifold to one of rank 1. You can approximate. So this and this doesn't change anything. So the same idea of deforming takes you from a non-regular Weismann manifold to a quasi-regular one. That is, from a Weismann manifold, a general one on which you don't know anything, to one which fibers in tori over a projective orbifold. And this is how you do it. So again, you can deform to quasi-regular, and then if the manifold is quasi-regular, then you obtain you identify it like this. It's clear. You take the orbifold. You take it is a projective orbifold. So you have this line bundle, and you take total space of this bundle. You get rid of the zero section, and that's it. And this is the relation between Weismann geometry and algebraic geometry in this way. Maybe I'll stop here because it will be too long now to go on there. I just wanted to tell you what the topology is. First of all, the Morse-Novikov cohomology vanishes. But there are also other properties. This was old. This is an old stuff. Um, but this fact that you have the flow of the Lie field acts trivially on the Botcher and Dolbeau cohomologies. This is very new. Nikita Klemyatin. And yeah, we have a complete description in terms of basic forms with respect to the canonical foliation of the cohomology of Weismann manifolds. So it decomposes in one part, which accounts for the cohomology of the transverse to the Lie field, and this part. And the cohomology of the transverse to the Lie field is clearly described in terms of the SL2 action on the cohomology. You can have the same thing for Dolbeau, but it's even more involved to be written. Again, for the harmonic forms, you can decompose it like this. That was old, but we have new proofs in so this decomposition of harmonic forms usually is used in dimension 1, but in degree 1, but it stems in all dimensions. And that's it. I think I have here a list of conditions, old and new, more of them new, for an LCK to be Weismann, but they are always sufficient conditions only. And this is important. Nicolina has this nice condition. The first one, obviously, is very important.